Thank you very much. Thank you all for having me here today. It really is an honor to be here. My name's Tom. JSConf EU is a very special conference for me. I was here about 4 years ago, which is where I met Zara, who you saw earlier. Jed introduced us on the plane. And 2 years after that, I proposed. And we're getting married in August. So for me, in particular, JSConf EU has been particularly life-changing, and hopefully many of you can develop similarly special relationships professionally, I mean. So today I want to talk to you about smartphones. And in particular, I want to talk about how tools that grew up on the desktop, like Ember, Angular, and React, can make the jump to the mobile future. And I think when people think about adapting apps to phones, they often focus on the more obvious differences. So for example, things like the difference in screen size, the difference in CPU performance, the different input devices, touch versus a mouse. But I think where the device is used is important too. So for example, a user on a mobile phone is more likely to be distracted than someone who might be focused on a task at their desk. Or they might have a more intermittent network connection than having a broadband Wi-Fi router in their apartment. So when phones can be used anywhere, there are very few assumptions that we can make, whether that's how attentive the user is or whether they have that internet connection at all. I recently started working at LinkedIn in December. And one thing about working at a site like LinkedIn is that it reminds me of how truly global the web can be. In many cases, adapting to smartphones really means adapting to new users. For many people, their first computer is a smartphone. That means millions, maybe even billions of people are going to be participating online without ever owning a desktop computer. And the more global your app is, the more combinations of devices and networks you'll have to deal with. CPU power can range from a feature phone to a low-end smartphone to the latest iPhone up to a beefy desktop computer. And network connectivity can range from GPRS to gigabit fiber to not being there at all. Just ride the subway in New York. So the problem with this is that without careful design, it's easy to optimize for one combination at the cost of another. So let's take a look at two different users. Let's imagine these two scenarios. So user A has a very low-end smartphone. It has a CPU that easily overheats and starts throttling itself. And they've got flash storage that is so slow that it would be borderline useless, except for the fact that it's already full. This person's data connection is quite slow, so they use Opera Mini, which uses a proxy to heavily compress all of the assets that their browser requests before the phone actually gets it. Now, user B has a high-end phone with a CPU that might rival a laptop computer. And they've got plenty of fast storage. The only problem is that this person is traveling without any cellular data. So while they may sometimes have access to broadband internet, it's only when they're in range of a Wi-Fi network that they can do anything useful. For user A, anything that requires a lot of JavaScript is probably not going to work at all. Even if they stopped using Opera's proxy, the slow CPU and storage means that downloading and evaluating a bunch of JavaScript is going to take a really long time. Getting reasonable load times probably means rendering on the server and keeping the file size of everything as small as possible. For user B, we want our web app to work more like a native application. In fact, we'd be willing to spend more time up front to load the entire app and as much data as possible onto the phone. It's basically what the App Store does, right? If that meant that we could still use it when the phone was away from this Wi-Fi connection that we're relying on. And this user probably has higher expectations of our app as well. It would probably be worth sending a little bit more code if it means that they get 60 frames per second scrolling and buttery smooth animations, since their hardware can definitely handle it. So best experience on the slower device is often radically different from the best experience on the faster device. And the problem is that historically, the more that we've tried to take advantage of high-end phones and fast networks, the worse that we've made the experience for the majority of the world. So what do you all think is the solution to this problem? I'll give you a hint. The initials are PE. Any guesses? What do you guys think? Shout it out. That's right. Panic and evacuate the building. Very good. No, the answer is supposed to be progressive enhancement. But one thing that's implicit, at least in all the advice that I've received about progressive enhancement, is that you're supposed to do it yourself. It almost always means rendering on the server and denying yourself the temptation of using too much JavaScript. And browsers, in the last 10 years, let's say, have advanced at a remarkable rate. To me, it feels like the web has never had more momentum, adding feature after feature. And yet, despite all of this incredible innovation, from IndexedDB to web workers, it doesn't actually feel to me like the experience of using web apps day to day has improved that much in the last 3 or 4 years. So why is it that these radical improvements in the browser don't seem to be translating into radically improved web applications? And I would argue that the reason for this is that the cost of code is too damn high. Taking advantage of all of those new features in the browser requires a lot of code. Native apps that work offline with beautiful user interfaces are hundreds of megabytes. And that's not even factoring in the SDK that ships with the operating system on the phone. On the web, just parsing and downloading JavaScript can be enough to turn some phones janky. And when you bundle all of your JavaScript into a single file, every byte starts to count. And in turn, this sets up misaligned incentives where libraries have to compete on file size rather than robustness. So how do they achieve these improbably small file sizes? Often, it's by persuading you that the old thing is unnecessarily complex, the cardinal sin in JavaScript. But they have seen through the BS and built something simple. And that leads us to the JavaScript simplicity fetish. It is this emphasis on file size that leads the JavaScript community to this fetish. When file size relies on simplicity, and speed relies on file size, and speed is paramount on the web, we have to pretend that simple tools are the best tools, because what other choice do we have? The only way to write an app that will run well on slower phones and networks is to ship less JavaScript. Too often, that comes at the expense of handling edge cases or building higher-level abstractions. As a community, we often feel like we can't build those sophisticated solutions because eventually we start to collapse under our own page weight. That's rational. We've seen this play out several times now. More sophistication equals more code equals slower load times. So the time period from 2011 to 2017 can roughly be broken up into the Backbone era, the Angular era, and the React era. Now, this trio of eras is also sometimes known as the Ember era. Now, it's easy to become enamored with the simplicity of a tool, and that can lead us to underestimate the complexity of building modern web apps. So let's take a journey all the way back to 2011, when the most cutting-edge tool that people were using was Backbone. And that people loved Backbone. I heard people say, I love it, it's so simple, I can clone it from GitHub and read the entire source code, all the source code in a day. But then I realized that whenever a model changes, every view in my app is re-rendered, right? Terrible performance. So what are we going to do about this? Well, I heard about this new library called Angular. It's really amazing. Two-way bindings feel like magic. It's so simple. You just change it, and it updates on the screen. But a year into the app, they thought, my app consists of one controller with 3 million lines of code. This doesn't feel very maintainable. But don't worry, because we have something called React. React is amazing because, and it's so simple, because it's just the V in MVC. And a year or two into building your app, you realize that it's 7 megabytes and takes 2 years to build. So Don Norman, who you may know as the author of The Design of Everyday Things, wrote this in an essay about security. The numerous incidents of defeating security measures prompts my cynical slogan: the more secure you make something, the less secure it becomes. Why? Because when security gets in the way, sensible, well-meaning, dedicated people develop hacks and workarounds to defeat the security. For example, when password rules are too annoying, people will just write down their password on a piece of paper and put it on their desk. So this prompts me to offer the Tom Dale simplicity corollary, the simpler you make something, the less simple it becomes. Because when simplicity gets in the way, sensible, well-meaning, dedicated people develop hacks and workarounds to defeat the simplicity. So how do we break out of this local maxima? How do we write one app that can somehow scale up and down across all these different devices and performance characteristics? Well, I think we can learn from native developers, because they've had to tackle a similar problem. So this is a bunch of different CPU architectures, and different CPU architectures have different instruction sets. If you write some assembly code for x86, let's say, and then you want to run it on ARM, you have to start over from scratch. They're just totally different. But learning assembly for all of these architectures is a really big task. If this is how system software was written, there probably wouldn't be much cross-platform code. And introducing new CPU architectures would be borderline impossible. We figured out a long time ago that a compiler can take a higher level program and get it to run across all of these architectures. And if a new architecture comes along, you just have to update the compiler and not rewrite every app in existence. So here's an example of using Clang and LLVM to take some C code and targeting an architecture that definitely didn't exist in the 70s, which is WebAssembly. And best of all, the compiler not only makes our code run on all these different architectures, it can also use its knowledge of different architectures to optimize our code differently for particular performance characteristics of that platform. So, for example, here's a paper about optimizing GCC, where they said, finally, a new target-independent feature could be implemented to take into account certain specific features of the target. For example, to make advantage of speculation feature of Intel Itanium, it's dating the paper here, we have implemented its support in the instruction scheduler. And this is something that Ashley said in her talk, which I just totally agree with. If there's one thing I want you to take away from this talk, it's that modern web toolkits are transforming from libraries into something that's more like a compiler. Except instead of compiling a higher level programming language into native code, they're compiling your higher level app into a highly optimized version. And eventually, I think, this will mean building multiple versions of an app and delivering the most optimized versions for that device. This might be as simple as delivering ES6 builds to newer browsers and transpiled ES5 for older browsers, or it could be something like automatically transitioning between server-side rendering and client-side rendering based on the network speed detected. But most importantly, these tools can finally embrace complexity by decoupling it from file size. If we can shift the complexity from to our build tools rather than being in these kind of monolithic runtime libraries, we can actually eliminate this enormous pressure to be simple. So unfortunately, I don't have a lot of time with you today, but I wanted to highlight three things that the teams behind React, Angular, and Ember are working on that demonstrate that these frameworks are staying relevant on mobile by essentially becoming compilers. So the first thing I'll talk about is React, and Ashley also mentioned Prepack, which is an open source tool from Facebook for optimizing JavaScript evaluation. Now, fortunately for me, Prepack was released while I was literally on the plane to Berlin, so I had to rewrite this part of the talk. But it was almost too good to be true, given that it definitely fits the theme. The Prepack website uses quite a bit of computer science terminology to explain what it's doing. It's genuinely very exciting and very novel. But you don't need to understand terms like symbolic execution or heap serialization to understand why Prepack has the potential to be a critical tool for optimizing web apps. So to understand why Prepack is cool, let's take a step back and understand how a bundle optimizer like Rollup works. The way Rollup works is by starting with an entry point file and analyzing which files it imports. So for each of those files, it then looks at what that file imports and so on, building up this tree. Once it's analyzed the entire graph, it builds a new JavaScript file that includes just the modules that were actually used. And then once we've analyzed that, we can get rid of the stuff that we don't actually need. Now, here's an example from the Rollup REPL on the Rollup website. All of our modules are on the left, and the final output is on the right. Everything we've imported is inlined right into that file, and modules that are never imported are excluded. This gives us smaller files by eliminating the files that we don't actually use. But it's not just modules. Rollup can do some really smart things if it sees exports that are unused. In this case, note that here that we've added a new class to animal.js, but our output on the right remains the same as before. That's because rollup is smart enough to not include the feral animal class, even though animal.js is imported, because no one actually asked for that specific export. This kind of thing is possible because module syntax in JavaScript was specifically designed to be statically analyzable. Static analysis just means figuring out things about how a program will run without actually having to run it. Rollup isn't running your code, it's just scanning it to figure out what gets imported and what gets exported. And modules don't actually work inside conditionals. So if rollup sees an import statement, it knows with 100% certainty, yeah, we're going to need this module. So that's rollup, which uses static analysis to optimize file sizes without running any code. Let's take a look at V8. Let's look at, or specifically, I mean, really any JavaScript virtual machine, but we'll look at V8 specifically. V8 can't help you with file size. By definition, it has to have downloaded the JavaScript files already. But it can help with making your code faster. So this is a high-level view of the architecture of V8, and there's 3 major components. I think there are V8 people here, so please forgive me if I get anything wrong. The parser, which turns your JavaScript source code into data structure. Then the interpreter, ignition, which evaluates your JavaScript. And finally, turbofan, which is an optimizing compiler, and which turns your JavaScript into optimized native code. Optimized code takes more memory, and it takes more time to generate, but it can run at truly ridiculous speeds. And as your program executes, V8 keeps track of which parts of your code get run the most and how they run. Based on this information, it will ask turbofan to create optimized versions of the code that it thinks will help your app run faster. So this is a kind of dynamic analysis. V8's optimizations require running your program. And that's a good thing. It's a JavaScript VM. Not running JavaScript would probably be considered a bug. But because it relies on how the program actually runs, you have to use the unoptimized code for a while until V8 can make some decisions. And that means that things will take a little while to get really fast. And every user pays that cost, even though the end result is more or less the same for everyone. So this is the fundamental tension that we have between static analysis and dynamic analysis. Optimizations that use static analysis can be run at build time, meaning you pay the cost once and all of your users benefit. But static analysis can only get you so far because you can only perform optimizations you're 100% sure about. If the module might get used, rollup can't remove it because if it guesses wrong, the app breaks. Optimizations that use runtime analysis can collect information about how a program actually runs so they don't have to guess. But requiring the program to run in order to optimize it is a bit of a catch-22. By definition, it means that the first run of the program will be running unoptimized, and that's the opposite of what we want on the web, where things typically feel instant. So that's what makes Prepack so cool. What it does is actually run your code. Similar to V8, it's an actual JavaScript virtual machine. Rather than running apps, though, it's designed to run at build time, and then it reverse engineers a simplified version that is faster for your user's JavaScript VM to run to execute for the first time. So this whole thing is a talking to itself, and I'm still digesting how it works internally. But let's just take a quick look at how it works. I know Ashley showed an example also. So imagine we're writing a library that prints the start date of JSConf EU. To create a new date object initialized with the start date, and then use that date in a string. So if we run this through Prepack, you can see that it's replaced all of that code with a single string literal. It's the final result of what we would have got if we'd actually run the code in JavaScript. But now instead of every user having to allocate a date object, parse a date string, initialize a date object based on that string, generate a full ISO 8601 date string, and then concatenate it, we have this simple string literal. And this is a contrived example. It probably wouldn't make much of a difference in reality, but each of these small savings may start to really add up in code bases the size of Ember, Angular, or React. And the good news is I've heard rumors that Jason Miller, who's here, will soon be releasing a new library called Prepack. It does everything that Prepack does in only 600 bytes of code. So let's take a look at Angular. Angular bet early on TypeScript, a language that personally I'm a really big fan of. And if you're not familiar with TypeScript, it's just a superset of modern JavaScript, but extended with type annotations. And those types make refactoring much easier, particularly as your project grows, as well as giving you incredibly rich autocompletes in your text editor. But to me, the most exciting and underappreciated reasons for introducing types into JavaScript is the potential for using that type information to more aggressively minify our builds. So let's take a look at how a minifier like Uglify works. Minifiers use their knowledge of JavaScript to make changes that don't affect behavior. So in this example, we've renamed this variable fruit to be called O. And because the variable is inside this function scope, nowhere else outside of that function can access it, so whatever we call it is kind of arbitrary. Let's change this example a little bit, and instead of making fruit a string, we make it an object with a name property. And even though the variable fruit still gets mangled, as you can see, the property name stays the same. Now, Uglify.js has a property mangling feature that you can optionally turn on, but unlike renaming variables, where it doesn't affect how the program runs, renaming properties can break things. In fact, the README of Uglify says, note, this will probably break your code, which doesn't instill a lot of confidence. So, for example, if we have an element and we change its onClick property, if that gets renamed to something else, then this is just going to fail silently. That click handler that we thought we were handling just doesn't exist anymore. Similarly, if we look at a component, this is like a React component, for example, there are parts of this object that are private, just to that component, and there are other things that are public, meaning that things like a library or the platform rely on it. Really what we want to do is mangle the private stuff, but maybe make sure that our library can keep using the public stuff. And there's good news. Google's Closure compiler already supports this kind of advanced minification for JavaScript. Unfortunately, it requires annotating types with JS comments and other weird Closure-specific configuration. Approximately 7 people on the planet outside of Google have actually got this to work. Now, the Angular team has released an amazing tool called Sickle that translates a TypeScript project into the format, the bizarre format that Closure compiler expects. So by using this extra information that TypeScript provides, and because Angular is written in TypeScript 2, Closure compiler can do some shockingly advanced minification. As the README says, the goal of this project is to let you write TypeScript and let Sickle handle massaging it into something that Closure compiler understands. And I'm really excited to see Googlers working on making Closure compiler's underappreciated power more accessible to the broader world. And integrating this into ngCli by default would, I think, make a huge practical impact into the final size of basically every Angular app. OK, so lastly, I just want to talk about Ember, and specifically Glimmer, which is the rendering engine in Ember and also a library that we extracted to be used standalone outside of Ember a month or two ago. Now, when you're thinking about the performance metrics of a rendering engine in the browser, there's 3 things you want to consider. The first is how long does the library take to load? So the fastest rendering library in the world probably wouldn't be worth it if it was like 50 megabytes, right? But then once you have something within a reasonable bound of time, you want to look at how long does it take to render a component for the first time when you have to create brand new DOM elements. And third, how long does it take to re-render a component, updating its existing DOM elements instead of replacing them when the data backing that component changes? OK, so who remembers this app? Yeah, the DB bane of my existence. This is Ryan Florence's dbmon demo app, which highlighted the benefits of React's virtual DOM diffing strategy. And for a while, it set off this frenzy of performance benchmarks, and everyone was competing to have the fastest score on it. And it's all anyone ever focused on. But then more recently, the community's focus has been on initial load times, as people have grappled with how we deal with these low-end phones and slow networks. And the tricky thing is trying to find the sweet spot that balances between optimizing the first render and optimizing re-renders. Fundamentally, this is an issue of bookkeeping. The more bookkeeping you do in the initial render to make subsequent updates faster, the longer that initial render is going to take. So consider a React component using Bootstrap markup in the JSX. On initial render, virtual DOM nodes are going to be created for each element here. And that makes a lot of sense, right? This is basically just instructions for how to create the real DOM. But if a single prop changes, we have to run the entire render function again. And that's quite a few allocations of virtual DOM objects, not to mention that once you have them, you then have to do this diffing step to kind of reverse engineer what changed between the last render and this render. So this example is small enough that the performance cost is probably negligible, but in large apps or inside a loop, you can imagine that it starts to add up. So can we do better? In Glimmer, we use handlebars templates for components, and these get compiled when you build your app. The question is, what do we compile them into? In Ember's history, the answer to this question has changed 3 times. First, it was strings, then DOM, and now with Glimmer, into a bytecode. So we tried an approach that we thought could balance the fast initial rendering of JSX while improving on the update performance. And we did it by treating handlebars and the entire rendering pipeline, actually, as though it were a programming language and a virtual machine that runs the compiled code. So in Glimmer, we compile this template into a JSON object that looks like this. Now, this probably doesn't look meaningful to you, but what this object represents is actually a sequence of opcodes, or instructions that tell the Glimmer VM how to build a DOM structure. We represent the opcodes in this compact data structure of arrays, integers, string literals. So parsing is fast, and memory consumption is much lower. When we landed Glimmer in Ember 2.10, many apps found that their template sizes dropped by 70 to 80%, which is pretty significant. Now, if you look closely at this, like I said, it doesn't really look like very much, but we use integers to represent instructions for compactness and for certain V8 optimizations. But if we were to represent it in a hypothetical Glimmer assembly language, it might look something like this, just a linearized set of instructions. So when we take those instructions and we execute them on top of the Glimmer VM, it looks a little bit something like this. We have an instruction pointer that just goes through this sequence, and so this is going to build an li element. Then we're going to move on and run the static adder opcode, and that's going to set the attribute, and then we're going to add another static attribute, which is the active class. And then that's the whole template, right? So now we're just going to flush the element, which basically tells Glimmer this is good to go to put into the DOM. Now, this is an easy example because it's completely static. But what about something that has some dynamic content? Well, what I haven't mentioned yet is that the Glimmer VM is actually made up of two VMs. One is optimized for constructing and appending DOM elements on initial render, and the other is optimized for updates. So this is the program for initially rendering this template. Now, we could run this again for updates, right? But there's a lot of static content in here, and spending time executing opcodes for static content that we know hasn't changed doesn't seem like a good use of time. In fact, we just want to focus on this dynamic part. And the way that we optimize this is through a technique called partial evaluation. And partial evaluation simply means to generate an optimized program by evaluating an initial program. And we use this technique to generate an updating program automatically. So essentially, as the initial rendering program is being run, we're generating a second, more optimized version to update the DOM for us when the data changes. Essentially, these operations in the initial rendering program are responsible for generating their own subsequent code. So the way this works is that we're going to go through our opcodes for the initial render as before. It's going to open a new div. We're going to set some static attributes on this. But now we're going to get to the dynamic content portion. And in addition to actually appending that content, that text content into the DOM, we're also going to generate an updating opcode, which is to update that content. And it's going to include a reference to which value we're putting in it, as well as a reference to that text node that we've just created. And then we'll flush the element like normal. Now, when that data behind the component updates, instead of going through that whole process again, all we have to do is evaluate our highly optimized updating program, which is just going to take the old data out of the DOM and update it. And you can think of it as doing something, it's a little bit more complex than this, but you can think about why it ends up being quite fast, because all you're doing is comparing these two values to see if they've changed, to know if you need to update the DOM. And we noticed that basically all the rendering library benchmarks only tested pure dynamic content. But that's not actually representative of most apps in the real world, where you have plenty of divs and other semantic markup. So we created a benchmark that had a mix of both static and dynamic content. And what we noticed is that initial rendering was more or less neck and neck with virtual DOM-based libraries. I'm not putting the other names here because it's not a competition. I just wanted to show that we're basically in the same ballpark. However, when we moved to measuring updating performance, what we noticed is that it seems that having this optimized updating bytecode makes a big difference when you're updating these components, which can make a big difference, especially on lower-end phones. So today, we've talked about 3 popular frameworks and some of the things they're doing to improve performance on mobile devices. It's important to understand that modern frameworks are becoming optimizing compilers, not just something that you drop into a page with a script tag. And this is just the beginning. There's an exciting trend towards more sophisticated tools that can analyze your app, perform optimizations that would be time-consuming, if not practically impossible to do by hand. Best of all, code that clearly conveys intent to other humans has a funny way of being able to convey intent to these optimizing compilers, too. So in 2017, the idea that build tools are optional, in my opinion, is totally outdated. A sophisticated build process is the backbone, ironically, of a modern web app. This morning, Addy showed a bunch of techniques for measuring and improving the performance of your web apps. That's awesome information. But not everyone can have Addy standing over their shoulder and reminding them to care about performance and to spend the time learning all these techniques. So I'm incredibly excited about a community that could build tools to help democratize and commoditize that performance know-how. So the best part of approaching frameworks as compilers isn't just that they help today's apps become accessible to more people. By reducing the cost of code, we can build better apps that don't collapse under the weight of their own complexity. By reducing the cost of code, we can finally dispense with an idea that I hate, that developer happiness and user happiness are somehow inherently in tension. This is a very exciting time to be a JavaScript developer. I, for one, am really looking forward to web apps that load instantly, work offline, feel great to use for everyone. Thank you.
Thank you, Tom. The tie really made it. Really did.